I'm going to make a short little video here on what's known as the Hall effect. The mathematics is described in the textbook, and I'm not going to get into the details of that, but more the description of what causes the Hall effect. Turns out this is a really important property of charged particles, and one that's very useful. In fact, our magnetic field sensors that we use in the lab are considered Hall sensors because they measure a magnetic field sort of indirectly by measuring a voltage across a plate like this. So let's take a look at what we have here. We have a metal plate, and the dimensions of this metal plate would be known. We just actually consider that a form of a wire, but that metal plate actually is going to have current running through it. And in this particular situation here, the current is running this way. But what's important is to remember that conventional current like this is the direction that positive charges would be moving, but in reality, we have electrons flowing in the opposite direction. So we will call this the electron current. And it's important that you describe what happens to the electrons here. So we're going to picture these moving kind of back to front. And that's the motion of the single electrons. And there's a magnetic field, which in this particular diagram is shown to be upward. So the Hall effect uses the property known as the Lorenz force. The Lorenz force is the force that acts on every moving charged particle when it's in a magnetic field that tends to push it in a direction that is perpendicular to both the motion of the particle as well as the field. So if we use the right-hand rule here, we're going to use the right-hand rule even though they're negative charges, and then we're just going to reverse the direction. So what you would do is you would point your fingers in the direction of the electron movement and then spin them up, the right-handed finger, spin them upwards to point towards the magnetic field direction. And what you'll notice is that your thumb should be pointed towards this side, the left side of the metal plate. But because these are negative charges, what we know then is the magnetic force actually pushes the negative charges to the right side of the plate. So the end result is that we get a collection of negative charges here on the right side, leaving a deficit of negative charges, or we could just think of those as positive charges, over here on the left side. And anytime we have a separation of charges like that, you might recall something like a parallel plate capacitor, we have a potential difference between them. And if we put a voltmeter across those two sides of the plate, then we will measure what is referred to as the Hall voltage. And that Hall voltage is proportional to how big the magnetic field is. It also is going to be determined partly by how big the current is and the dimensions of the plate that we're using. But again, I'm not going to get into the details of the mathematics. So we are able to create a voltage just by virtue of moving these charges through this plate. That's what's called the Hall effect. And another way to do this would be to take the whole plate itself and move it, like pick it up and move it in the same direction that the current would be moving. We would also see the separation of charges happen in that situation. So that's what the Hall effect here is. It's just a kind of a consequence of the Lorenz force, not much more than that. So as long as you can do the right-hand rule, you're probably able to figure out just about anything you'd be asked concerning that. So I think we'll leave it at that.